Thank you, Jamie, for the very nice introduction. I'm Kamalika Chaudhuri, and I'll be starting off this tutorial. Okay, so just some quick logistics. The tutorial time is, our speaking time is going to be about 2 hours, so there would be a 10-minute break after the first hour and, 5 minutes at the end. So what are we planning to do in this tutorial? Well, our goal here is twofold, right? So first we are going to motivate and define differential privacy so you understand where it should be used, where it shouldn't be used, what is the context in which you can use differential privacy and what kind of privacy it's going to give you. Second, we are going to provide an overview of common methods and tools that are currently used to design differentially private machine learning algorithms, right? And what we will not be able to do due to the huge volume of work in this area is we will not be able to provide detailed results on specific problems, and especially on the state of the art or detailed results on specific problems. Before this tutorial, I did a quick Google of differential privacy, and what I found is since 2016, there has been 2,300 hits on, 2,300 new pieces of work on differential privacy. So you understand that it's not possible for us to cover these things in detail. And at the end of the tutorial, you should be able to, understand and explain the definition of differential privacy, design basic differential privacy machine learning algorithms using standard tools, try different approaches for introducing differential privacy into optimization, then understand things like the basics of how to account for privacy risk when we touch the data multiple times, and then understand how to put all these ideas together in designing more complex differentially private machine learning systems. Okay? So without further ado, let's start with motivating differential privacy. Okay? A lot of data these days that machine learners must work with is really sensitive data. So examples would be things like medical records or genetic data or search logs, for example. What happens when we don't think about privacy issues in this data? Okay? And to give you an example of the kind of things that can happen, let me start with an anecdote. So in 2006, AOL, which at that time was a search company, they had a search engine, they decided to, they wanted to improve search, so they decided to make a data set available for, academic researchers and the general public, right? So they wanted to make this data set publicly available, and what this data set had was for every user, they would replace the username by some random ID, and then they would have a list of things that the user had searched for, okay? And here is what happened within, the next day, right? So this is a New York Times article which came out the next day, and it took the reporters just a few hours to discover the identity of a few people in the data set. And this picture is of a lady who had agreed to be interviewed for this article. There were a few other people who didn't agree. And this was just with a few hours of effort, and if they had looked into putting in even more effort, even more people would have been identified. Okay? So this is kind of what happens when you anonymize data. Another example is, the Netflix competition. So, this is a machine learning crowd. I'm sure most of you have heard about the Netflix competition, which was which was pretty much the first, public kind of big data competition, right? So there what happened was that Netflix wanted to improve their movie recommendation system, and what they did was that they released a data set which looked like the following. For every user, they had a list of movies that this user had watched and how they had rated these movies, along with some extra metadata like approximate dates when the user had watched it and so on. And Narayanan and Shmatikov looked at this data, and what they could show was that if you knew just a few movie ratings and approximate dates for somebody in the data, then you could figure out for let's say somebody, one of your friends, you could figure out whether your friend was in the data set or not. And if she was in the data set, you could figure out her other movie ratings that you might, that she might not have revealed to you, right? And this is, and it's not a lot of extra information. So for example, if you read somebody's blog, maybe they have blogged about a few movies that they like, this is quite reasonable information for people to know, right? It's not like a great deal of extra information. So why did this happen, right? So why do we have this kind of thing? Well, here is kind of a toy example which shows why, right? So what happens is, the reason why anonymity doesn't work is because high dimensional data about people tends to be extremely unique, right? So let's say my employer, UC San Diego, decides to release a salary table of employees, and you see a row of the table which looks like this, right? You have faculty, and gender is female, department CSE, and ethnicity Southeast Asian, and you immediately know that there is only one person who fits this description, okay? And the linkage information, which is the information which connects this table to me, that information is in fact publicly available on my department's webpage, right? So if you go to the CSE department's webpage, you have a list of faculty with their pictures, you immediately know who this person is, okay? So this data is very unique. So the reason why it's a big problem is because, one, this kind of high dimensional data about people is very unique, and two, the linkage information is often, readily available and searchable and so on, okay? And so what this means is that if you simply anonymize data, that is unsafe. Okay? How about statistics on data? So this is another study which was done by Wang et al. In a paper in CCS 2009. So what they did was they looked at disease association studies, okay? And here what they had was they had two groups of patients, a group of cancer patients and a group of healthy people, and they looked at SNPs of these patients, and they looked at pairwise correlations of the SNPs, right? So for every SNP pair, they looked at how correlated they were across two groups, okay? And what Wang et al. Showed was that simply based on these two tables, you could figure out, and if you knew something about Alice's genetic profile, you could figure out whether Alice was in any of these tables or not, and you could figure out which table she was in, right? And so, what happened over here? Well, essentially what happened was that you had, they had a lot of SNPs, so something like a few thousands of SNPs, and then they were looking at pairs. And these tables were built on a few hundred people's data. And this is, by the way, very reasonable for the genome-wide association studies because their data is very expensive to collect. So they had lots of SNPs, not enough people involved. And so, now you know what the problem is, like lots of equations, not enough unknowns, so they could figure out what was going on, okay? And in general, so what this means is that, simply anonymizing data is unsafe, but also if you have lots of statistics on small data sets, relatively small data sets, even that can be unsafe. And as we'll see throughout this tutorial, there's a trend where there are three things that are going on, right? So there's privacy, which is, of course, privacy of individuals, data size, which is the number of subjects or number of people involved in the data, and accuracy, which is how accurately you can calculate calculate statistics on these individuals, okay? And generally what happens is you can get two corners of this triangle, but not all three. Okay, so if you want to get both privacy and accuracy, you need a lot of data, and vice versa. And different algorithms differ according to what the trade-off between these three factors are, right? So what the trade-off between privacy, accuracy, and sample size are, okay? Okay. So, at this point in our story, what is happening is, statistics on small data sets are unsafe. What is small data sets? What kind of statistics? So this is, these are getting to be really complex questions. So to deal with them, we need to have a rigorous definition of privacy, which is what I will be talking about next, okay? So let's look at, before I go to the privacy definition, let's look at the setting. So there are, there are other privacy settings available, but this is the setting that we will be focused on for pretty much the whole tutorial, okay? So here is the setting. You have a private data set, okay? And then you have some sanitizer, right? So a sanitizer is something which takes as input a private data set and then outputs stuff about the data sets, let's just say, right? So it can output things like a summary statistic, it could output a synthetic data set, or it could output some machine learning model that it calculated out of the data set, and so on and so forth, okay? And between the sanitizer and whatever comes out of it, there's a privacy barrier, right? So in some sense, on one side, on the I guess to your left of the privacy barrier is things that are not visible to the public, whereas to the right of the privacy barrier are things that are visible to the public, okay? And so this is our setting, okay? So what kind of properties that do we expect the sanitizer to have? Well, what the sanitizer kind of wants to do is it wants to make aggregate information about the data set computable, right? So things like population properties about the data, should be relatively accurately available across the privacy barrier. However, individual information should be protected. And so, information about, specific people in the data should be protected. And this should be also robust to side information, because people do have side information, linkage information is available and searchable. So this protection should be relatively robust to some side information that the adversary may have, okay? So how does differential privacy do this? Differential privacy says that the participation of a single person in a data set does not change outcome, right? So for example, if you had a data set which had Alice, and if you took out Alice and replaced her with Bob, the outcome would not change very much, okay? And so why is this focus on the individual? Well, the reason for this focus is because an individual has agency, right? So I might decide to participate in a database or not, depending on, what I think of the risks, right? So, our data set has a certain amount of, offers me a certain amount of privacy, and then I can decide whether to participate in it or not, right? And so, because the agency is at the individual level, that's why we focus on people level privacy, okay? So let's try to see what this really means by an example, okay? Suppose we have an adversary who is, let's say, a health insurance company, who has some prior knowledge, right? So they know Alice's genetic profile because Alice had some tests done at some point, and they also know that Alice smokes, okay? And this company is trying to determine whether Alice has cancer or not, so that they can deny her health insurance, or they can raise her premiums by a lot, okay? Okay, so here is a case study, right? Suppose the company looks at that study we talked about a little earlier, the Wang et al. Study, and somehow Alice happened to be in the study and in the cancer group. They reverse engineer from the S&Ps, they reverse engineer the values, and they figure out that Alice has cancer, right? According to differential privacy, this would be a violation of Alice's privacy, because if Alice was not in the data set, the adversary would not have been able to do this, okay? On the other hand, let's say the adversary, reads, opens the latest, suppose they open the latest, Science or Nature magazine, and they find a study that smoking causes cancer. And then they decide that, oh, I know that Alice smokes. Well, then Alice probably will, either has cancer or will develop cancer at some point in her life, and they decide to, deny her insurance, right? This, however, is not a violation of Alice's privacy in terms of the study, because even if Alice was not in the study, even then the adversary would have been able to conclude this, would have been able to conclude that she has cancer, okay? So this is not a violation, whereas the first one is a violation, right? So this is the kind of privacy that differential privacy provides, okay? So remember, this was, our overall idea that participation of a person does not change outcome. How would we ensure this? So the way differential privacy will ensure this is through randomness. So it looks at two random variables, the output of an algorithm on data plus Alice versus the output of an algorithm on data plus Bob, right? And what they want to ensure is these two, the distributions of these two random variables are close. So where does the randomness come from? In differential privacy, the randomness is added extraneously by the algorithm. So A is a randomized algorithm. Whereas if you want to, and how is closeness measured? Well, to measure closeness, differential privacy uses the likelihood ratio, requires that the likelihood ratio at every point is bounded, okay? And so this finally leads to the definition. Here is what the definition looks like. So if you have data sets D and D prime that differ in a single person's private value, if A is an epsilon differentially private randomized algorithm, remember a differentially private algorithm has to be randomized, then the following equation holds, right? So the equation says that if you look at the likelihood ratio that A of D equal to T over A of D prime equal to T, take the log and the absolute value, then the supreme arm of this over T is at most epsilon, right? So which means that at every point, the absolute value of the log of the likelihood ratio should be bounded by epsilon. And for those of you who have seen this, so if you look at it a little bit closely, this quantity is in fact the max divergence between the likelihoods of A of D and the likelihoods of A of D prime. Okay. There is also another slightly relaxed version called approximate differential privacy due to Dec4 et al. And there the condition changes a little bit, and you have two parameters, epsilon and delta. So if you're for all data sets D and D prime that differ in a single person's value, if your A is an epsilon delta differentially private algorithm, then the following equation holds. Here you look over all subsets of outcomes with probability mass strictly greater than delta, and you look at the ratio of log probability that A of D lies in that set minus delta over probability that A of D prime lies in that set, and this log of this ratio has to be less than equal to epsilon. Okay, so this is the approximate differential privacy definition. Okay. So why is this a good definition? Well, differential privacy actually has a lot of very attractive properties, okay? And I will mention them very quickly now, and we'll get back to them later in the tutorial. So one extremely good property is what is called post-processing invariance, okay? So what does this mean? Suppose you have your private data set, and then you have a differentially private algorithm which crosses the privacy barrier. And then you take the output of a differentially private algorithm and you do a lot of post-processing that does not involve the private data again, right? You cross the privacy wall and then you don't touch the private data again. If that is the case, then your privacy risk is not going to increase. Okay, and this is quite an interesting property. The second property is graceful composition. Okay, so all private algorithms have the property that privacy, the more you learn from a data set, from a private data set, the more privacy erodes, and this is the case for essentially any private algorithm. Just to give you an anecdotal example, I read the blog of an academic who's pseudonymous, and I had been reading her blog for a long time, and then slowly I began to realize, oh, she must be here, and I found out one more fact about her, and then after a couple of years I realized I know who she is, right? And this is ubiquitous. You cannot avoid this problem. The more you learn about some private data, the more privacy erodes. But the good thing about differential privacy is that this privacy erosion is graceful. Okay, so what this means is if you have some, algorithm, differentially private algorithm, which gives you epsilon 1 delta 1, and then you have another one which uses the same data set and gives you epsilon 2 delta 2, then the privacy loss will be, the privacy loss will not suddenly rise to something huge, right? So for example, here, the example that I'm showing, the privacy loss is sum over I epsilon I and sum over I delta I. It's possible to do even better, and we will talk about that in a little bit. Okay, so we'll talk about tighter composition. So this is called graceful composition. We'll talk about tighter composition a little bit later. Okay. So good. Hopefully, I have convinced you now that differential privacy is a good definition, and this is something to aspire to. Now the question is how to achieve differential privacy. Okay. So what I will do is begin with a couple of tools for general differentially private algorithm design. So and the two tools I will talk about are called the global sensitivity method, which is due to Dec4 et al. 2006, and exponential mechanism due to McSherry and Talva 2007. There are many other, quite a few other general differentially private algorithm design tools, like proposed test release, smooth sensitivity, and so on. But for the purpose of this tutorial, I'm not going to talk about them. I invite you to go look them up. And we will talk about these two methods because we are going to use them a little bit later along the tutorial. Okay? So what is the global sensitivity method? The global sensitivity method works as follows. So what you want to do here is you are given a function f, a sensitive data set d. Your goal is to find a differentially private approximation to f of d, right? So remember, f of d is not going to be differentially private by itself, because if f is a deterministic function, so what you need to do is add some randomization in there, and what you want to do here is find a differentially private approximation to f of d. Okay, so an example of this would be, let's say you have a bunch of data points and f of d is the mean of these data points. Okay. So what does the global sensitivity method do? So it works as follows. It looks at the function f at the sensitive data set d, and we define the distance between two data sets d and d prime to be the number of records in which d and d prime differ, right? So if the distance is 1, that means that d and d prime differ by a single individual's values, right? And here a record is referring to a single person, okay? Then the global sensitivity of f is defined as the following. You look at the absolute value of the difference between f and f prime, the absolute value of the difference between f of d and f of d prime, okay? And where d and d prime are at distance 1, so d and d prime differ in one person's value, and you take the max of that over the domain, right? So the way to think about this is think about how the function changes as you change one record, and the maximum possible change in the value of the function as you change one record. Okay, so that is your global sensitivity. And so there are two variants of the global sensitivity method, which we will come and look at. There are more variants which I won't go into today. So one of the most common variants is called the Laplace mechanism. Here the idea is you take the global sensitivity, so S of f is the global sensitivity of the function f, and you compute the function on the sensitive data. So you compute f of d, and then you add noise, where the noise is distributed as follows. Okay, so the noise is the sensitivity divided by epsilon times Laplace noise with parameters 0 and 1. Okay, so if you, so just a quick reminder, the Laplace distribution, it has the following density. So the density of P of a Laplace random variable given parameters mu and b, where mu is the mean and b is a scale parameter, is 1 over 2b e to the minus absolute value of z minus mu over b. Right, so this is the Laplace distribution, and it looks like the PDF looks like the things in the picture, right? So these are two examples of two Laplace distributions, and so if you add noise z, which is the global sensitivity of f divided by epsilon times the Laplace 0, 1, then what you will get is something that is epsilon differentially private. Okay. So again, to achieve epsilon differential privacy, there are also other ways of adding noise, and in fact, if you want to minimize the mean square error, there are some sophisticated things that you can do, but we won't get into that right now. This is one of the very general major things that people use. Okay. The second variant is what is called the Gaussian mechanism. Again, remember the global sensitivity is S of f. And here what you do is you again calculate f of d, where d is the sensitive data set, and add noise to it, but now the noise is not a Laplace noise, right? And in fact, the noise is calibrated a little bit differently. The noise is the global sensitivity of f over epsilon times a Gaussian random variable with mean 0 and variance 2 log of 1.25 over delta. Right, and if you do some calculations, you can see that this is going to give you epsilon delta differential privacy. Okay, so remember we talked about approximate differential privacy, so this is going to give you epsilon delta. Okay, going back to our mean example, suppose we have a sensitive data set where every record is a scalar between 0 and 1, and the function f of d is the mean of these data points. Okay. Here, if you look closely, and if there are n data points, then the global sensitivity of the mean is going to be 1 over n, right? And if you use the Laplace mechanism, what you're going to do is you're going to, add to the actual mean a random variable z, where z is 1 over n times epsilon times Laplace of 0, 1. Okay? So there's a couple of things to note over here. The first thing to note is that this is in fact not really a lot of noise, right? So if you look at this Laplace 01 random variable, its standard deviation is kind of, a constant, right? And, if you divide it by 1 over n epsilon, if your n is large, this is actually, the magnitude is not in fact pretty high, right? Like this is a pretty small random variable, right? And, so for example, in this kind of thing, the sampling error itself would be of the order of 1 over square root n, and here you are adding something of the order of 1 over n epsilon, right? So this noise is not very high. The other thing to note is, again, if we were optimizing the mean square error in terms of accuracy, we could do much better. We would choose we could do a bit better, and we could choose a slightly different distribution. But again, the Laplace mechanism is the one which is widely used because it's nice and simple. Okay. Okay. So now we have looked at the global sensitivity method, and we have covered 2 of its variants, the Laplace mechanism and the Gaussian mechanism. Next, I'm going to go ahead and look at our second basic algorithm design tool called the exponential mechanism due to McSherry and Talwar. Okay. So what is the exponential mechanism? What does it do? It tries to solve the following problem. Okay. So you're given a function f of w and d, where d is our sensitive data and w is some other parameter. Okay. And what it wants to do is it wants to find the differentially private approximation to the maximizer of f of w and d. Okay. So it wants to find this maximizer. So an example of this is maybe W is some sort of classifier and D is some sort of a validation data set, and F of W and D could be the accuracy of classifier classifier W on this validation set D. Okay, so and what exponential mechanism would do is it would find the differentially private approximation to this maximizer. Okay. So a couple of things to note over here. So one is that, so a couple of things to note is, so one is that this maximizer, even if you are, even if you're outputting a maximizer, the maximizer itself could violate differential privacy, because if you change, if one person participates versus not, the function f of wd could change, and so its maximizer could change. An exponential mechanism tries to find this maximizer privately. Okay? So what does it actually do? Here is how it works. Okay? Suppose it so happens that for every w, the absolute value of the difference between f of wd and f of wd prime is at most s, right? And this happens when d and d prime differ in one record. If your function f has the following property, then the exponential mechanism will sample w from the following distribution. The probability of w would be proportional to e to the epsilon times f of wd divided by twice s. Okay, and if you sample from this distribution, then you are going to get epsilon differential privacy. Okay. So some of you guys are going to recognize this as sort of a soft max, right? So if you were finding the maximum, without differential privacy, that would be the hard max, and in some sense this is a soft max, right? Because if you look closely, the maxima of this density is in fact the actual maximizer, but it also has some sort of a variance, right? And the variance depends on epsilon and s. Okay. So essentially what you're doing here is you have a soft max. How soft the max is depends on what your privacy parameter is. So if your epsilon is really low, which means you have a high privacy, then it's softer, and otherwise it's it's not as soft. So that's essentially the exponential mechanism. Here is an example of what the exponential mechanism does. So this example would be, so for example, parameter tuning, right? So suppose you have some validation data set D, and you have k classifiers, W1 to Wk, which you got out of tuning k parameters, okay? And let's say what you would like to do is, your validation data set is private, and you would want to find the classifier with the highest accuracy on D, right? So here, your function fwd would be the classification accuracy of W on D. And notice, because of the way accuracy works, so we are looking at the 0-1 loss. So for any D and D prime that differ by a single record, the absolute value of the difference between the accuracies is at most 1 over the size of D, right? Because when one person changes, the accuracy of the same classifier could change by, 1 out of D, right? And so the exponential mechanism will look like the following. It will output classifier Wi with probability proportional to epsilon times the size of the data set D times f of Wi comma D divided by 2. Okay? So again, there are a couple of things to observe over here. So one thing to observe is the maxima is the maximizer, right? So this is sampling from some distribution. The maximum of this distribution, the mode of this distribution is the maximum, is the Wi at which f Wid is maximized. The second thing to observe is because you have epsilon times D in your exponent, what this means is if your validation data set is really large, then this function, then this density will be very, very peaked, right? So what this means is if you have a large validation set, then the maximizer that you would get out of it would be more and more accurate, and which kinds of ties in with our theme of privacy, accuracy, sample size trade-offs, right? So if you have the same privacy parameter, if you have a higher amount of sample size, then the result that you would get would be relatively more accurate. Okay, so this kind of ties into one of those parameters. Finally, again, it's, we will come back to this later. Here I have given you an example with discrete, where W is discrete. We have W1 to Wk. We can also run the exponential mechanism in the continuous case. So you can look at, W could be, there could be some kind of base measure on W, and then you can look at what happens after you see the data. And this is also done, but sometimes what happens is, these kinds of things are hard to implement privately because just sampling from the exact distribution gives privacy, and we can't really say anything about privacy properties of the MCMC methods unless they have converged. Okay, so sometimes this becomes a little bit challenging, but in theory you could also use it for continuous distributions. Okay. So to summarize, we talked about motivation. Why do we need differential privacy? When should we use it? We looked at what is differential privacy, and we looked at two very basic differential privacy algorithm design tools. Okay, the global sensitivity method and its two variants, and the exponential mechanism. And next, Anand is going to tell you about differential privacy in estimation and prediction.
She'll be back.
Okay, so I'm going to give the middle part of this tutorial sandwich. And I'm going to talk about differential privacy and sort of empirical risk minimization and gradient descent methods. So again, I'm going to, just to emphasize what we said before, we're going to sort of give an overview of kind of basic concepts. For more advanced stuff, you can look at some of the more recent references that we have in the application section. So what kind of problems are we interested in? We're interested in looking at estimation and prediction problems, and in particular statistical estimation problems in which you have some notion of statistical risk, which I can call W. So again, I want to pick some parameter W of my problem that's going to give me a low risk on the population that from which I'm sampling. And so we are going, this algorithm is going to have to take the private data and this risk functional and somehow find a way to minimize the risk in a differentially private way. And the goal is to minimize the excess risk. That is, if I produce an estimator W hat that's differentially private, I'd like to have its risk be close to the optimum risk, which is represented by W star here. So this is another example of this privacy, accuracy, and sample size trade-off. So the question is, how much data do I need to guarantee this objective? So just before we go on, privacy and accuracy measures are making different assumptions about the data, and that's kind of fundamental to differential privacy. And in differential privacy, from the privacy definition, we're making no assumptions about the data. There is no true data distribution, and we can't say, look at probabilities or events over some data distribution. We want these privacy promises to hold unconditionally. But however, if we're going to measure accuracy, we're measuring accuracy with respect to some possible population distribution. So we're going to actually look at this expected risk over, what if the data was generated from some unknown distribution, then can we bound universally over all such distributions the excess risk? So a very popular framework for doing these kind of problems is, of course, empirical risk minimization. So you take a loss function, which is representing your risk, and you minimize the average risk over the data set, maybe plus a regularizer. And so a concrete instance of this is, for example, training a classifier where W is a predictor, and in linear classification it'd be a vector, and X is your features, and Y is a label that you're trying to predict. So the question is, how do we introduce privacy in this setting? Or rather, maybe the first question is, what's wrong with this? Isn't this sort of already guaranteeing privacy? And I guess we can sort of say, from what we've seen before, it's a deterministic algorithm, so it's not providing any privacy. But we can see it sort of visually. So if I give you two data sets, D and D prime, which differ in one individual, then I can say, move Alice, who is this green positive label above, and move Alice, change Alice to Bob, and put her on the other side. Then the classifier boundary is going to change, and depending on what your data set looks like, it could change quite significantly. So it's very easy for an adversary observing the output of the method. The adversary gets a particular W that was produced by your method, and can easily tell, at least between these two alternatives, which data set was generated that classifier. So, okay, so this is linear classification. Kernel learning is like an even worse situation. Like in kernel learning, the classifier that you produce is actually a linear combination of kernel functions evaluated at your data points. So even to compute the label, you would have to reveal some of the data, which seems like a bad move from a privacy point of view. And even if you had sort of black box access, you could imagine schemes which would sort of repeatedly query this black box and then try to recover the data points. However, so this makes it seem like, learning problems are hard from a privacy perspective, but I'd like to sort of say that that's not true, because there's a lot of theory to suggest that privacy is actually very compatible with learning, in the sense that guaranteeing privacy is in privacy, you want your algorithms not to bend too strongly on individuals, and that's a good thing for your learning methods too. You don't want your learning algorithm to depend very strongly on individual data points. That would be bad. And so good learning algorithms really should generalize to the population distribution and not individuals, and similarly, privacy-preserving algorithms should depend on the population distribution, not individuals. And so there is a notion of this in machine learning already, right? There's this notion of stable learning algorithms. And so very now classical result says that if a learning method is stable, then it will generalize. And so we can actually interpret differential privacy as a form of stability. So it's a type of stability. It's a little bit different than the kind of stability that maybe was studied earlier, but it also, in fact, implies generalizations, a whole host of notions of stability here, which you can dig into. It's a very interesting story. And so I'd like to say that this is not incompatible with the kind of objectives we've been looking at before. These kind of guarantees are about asymptotics. That is to say that learning privately is possible. You're not going to end up with some residual bias. So privacy implies generalization asymptotically. But if you're looking at finite sample sizes, then you really do have this privacy accuracy sample size trade-off. So it's a difference between sort of asymptotics and finite n. Okay, so let's go back to ERM. So we have this convex optimization problem, assuming the loss is convex and the regularizer is nice. So there are kind of three steps when I'm going to train my classifier. I teach undergrads, when I teach undergrads, I say, okay, first you got to read in the data and pre-process the data, and then you got to form your objective function, and then you got to run some minimization method. And we can try to introduce privacy in each of these different places, and then we can see, whereas the question for differential privacy is where do you put the noise? Here's three steps. We can try to put the noise in one of the three steps, and hopefully one of them will be maybe a bit better than the others. So, and generically speaking, for sort of any kind of process which would go this way, read in the data, kind of form an objective that you'd like to minimize, and then do some optimization, we can look at general approaches to introducing privacy here. And so the first would be, think of it as input perturbation. That is, I could process my data set, introduce the noise there, and now it's a noisy data set, now it's private, and I can use that post-processing invariance to continue to do learning. I could also introduce noise somehow when I form the objective function. That is, I could perturb the objective function in some way. And finally, I could, maybe I don't want to go dig into my objective function, and I'll just run my standard machine learning algorithm and then use this, say, sensitivity method to kind of tweak the output a little bit, fuzz up the output, and that will guarantee differential privacy. So the question is, where do we want to add the noise? So we have a couple of different options, or you can think of these graphically in the pipeline. So here's my population of emoji individuals. The first thing I could do is I could say, well, when I collect the data from these people, I will have them add the noise for me. I'll have them randomize for me. And so they could do some kind of input perturbation there. They could randomly give me some answers. And then the privacy barrier would then exist between these people and the database. So now there's a sanitized database. Everything is protected, and I can run my favorite non-private learning algorithm because of post-processing invariance. I could also do some pre-processing, and so instead I could have them put their data, non-privately into this it's private database, and then I could do some pre-processing to kind of export a sanitized data set, and that's also, we can think of that as, and then run my favorite non-private learning algorithm, and I can think of that as also kind of input perturbation. Output perturbation would this is objective perturbation. Objective perturbation would involve, say, doing my pre-processing in a non-private way, and then somehow changing the optimization problem, introducing some noise there, and then solving that, and then publishing that across the privacy barrier. And finally, if I want to do output perturbation, I'll do the pre-processing and the optimization in a non-private way, and then I'll just introduce some noise or perturbation at the end, right? And then I can publish that across the privacy barrier. So the question is, what are the benefits and drawbacks from each of these approaches? Well, if this local privacy, this approach where people add noise to their own data, that's actually called local privacy. And so this is actually related to a very classical technique in statistics called randomized response. It's all the way back from the 60s. And you can look at interactive variance. This is a little bit beyond the scope of what we're looking at here, but there's a lot of interesting questions in the local privacy model. If I do input perturbation, I'm going to, the advantages here are that it's pretty easy to implement often, because what you're going to do is end up with a sanitized data set. So if I have a sanitized data set, then I can do whatever I want with it afterwards. I don't have to worry about privacy after I push it across the privacy barrier. So this means you can reuse it for all sorts of different things, and that could be an advantage. For output perturbation, the advantages are that you really don't have to re-engineer anything. You just use all of your standard algorithm that you're using before, but then you have to analyze how much noise you have to add to guarantee differential privacy. So if you can do a little bit of math, then you could be okay, and you don't have to re-engineer anything in your pipeline. And the noise here is going to somehow depend on the sensitivity of this optimization method. And objective perturbation is a little bit more complicated, so let's dig into what do I mean by this perturbing the objective function. So here's my objective function for ERM. It's the average risk plus this regularizer. And so there are kind of two approaches to thinking about messing around with this objective function. One is I could add a noisy term to it, that is going to add a random term to it. Here I'm adding a random linear term. And say minimize this new objective, which is a sort of tweaked version of the old objective. And the other would be to sort of use some randomized approximation, like in a functional approximation kind of idea, to sort of approximate the objective function and then minimize this approximate objective function. And again, we have to then understand, to analyze these things, we have to understand the analytical properties of this objective function. So essentially where it all boils down to is looking at how sensitive this minimizer is. If I look at non-private optimization, what am I doing when I just don't care about privacy, is I just take the gradient and set it to 0 and solve, right? And so if I look at this adding a linear term to the objective, I'm just going to add a linear term, and the coefficients are going to be randomly chosen according to this distribution here, which is kind of like a vector analog of the Laplace distribution. It's proportional to the norm of the vector rather than the norm squared, so it's not Gaussian. The private optimization is solving a slightly different problem. It's taking the gradient and then setting it equal to minus b. So I'm setting it equal to noise. So I'm solving the gradient equals now a noise vector, and that's going to give me my privacy. And somehow this solution of this problem, maybe it will end up smoothing out some of the pernicious effects of the noise, potentially pernicious effects. And we have to sort of bound this sensitivity then of this gradient function. That's really what it boils down to. Okay, so how well do these methods work? Well, you can do some theory, and there are a lot of parameters which are going to affect the performance of these methods. Obviously, there's epsilon and delta, the privacy parameters. There's the data dimension. There the bounds, how, if you normalize your data, and then normalization that you've done, stuff about the loss function like Lipschitzness and smoothness and so on, and also the regularization function and the regularization parameter. But I'm really just going to talk about dimension and privacy parameters just to illustrate the kind of results that one can get. So if I look at input perturbation, you can, in epsilon delta, so that's approximate differential privacy, you can get sort of you can see again that it's effectively like your sample size has been decreased by a factor of epsilon. I mean, this is true for epsilon less than 1. If I look at output perturbation, you get you can look at both epsilon and epsilon delta, so regular differential privacy and approximate differential privacy. And you can see the scaling here is different in the sense of the dependence on the data dimension. The dependence is much worse on the data dimension when you ask for the stronger privacy guarantee. And for objective perturbation, you get similar kinds of results, but a sort of milder dependence on the privacy parameter. So that's theory, but how does it work empirically? So empirically, you can do some experiments. You can take your favorite data sets like MNIST, or in this case, this is KDD Cup, and this URL data set from Abradeep's paper. So you can sort of take a few takeaways when you run these things in practice. Is that objective perturbation typically and empirically outperforms output perturbation in most cases. Another thing is that this weaker epsilon delta privacy guarantee, which you can get by adding Gaussian noise, gives much better performance, like significantly better performance than epsilon 0 privacy. And the other thing is, if you run it on more than 1 or 2 data sets, so more than MNIST and CFAR, then you'll really see that the performance is very data set dependent. So we kind of don't at the moment have a really great understanding of how well, if you give me a data set, how well it's going to work. So this really leads to some interesting gaps between the sort of theoretical story, which in the broad strokes tells you what's going on, and the practical, you're going to do this on your data. In particular, how should you choose epsilon and delta? That's always a big question that people ask, and I'm going to sidestep and say it's a nice question to ask, right? Okay, so don't ask me. Given a data set, what can I tell? Like if you give me a data set, maybe I can just kind of look at it vaguely. Can I tell what kind of epsilons I could get with reasonable utility, or reasonable accuracy? It's also not entirely clear, but that's the case in regular learning also. But the privacy makes it a little bit more complicated. What I showed is, results in things for ERM, but this is sort of generally, you can do more general convex optimization. There's been some work on this already, but you might have your own particular problem that you're interested in which we don't know the answer. And then what I'll talk about after the break is talking about scaling things up to larger data sets. So at that point, I think we'll summarize this section. So training, just to summarize sort of for ERM, training on its own isn't going to guarantee you privacy. And there are many ways of incorporating differential privacy into learning in this input and output and objective perturbation, but there's, you have to basically figure out where you're going to put the noise. Good differentially private algorithms should in fact generalize since they're about populations and not individuals, so it's not like, privacy is not a game killer necessarily. If you're going to go build your differentially private algorithm and you're willing to tolerate epsilon delta differential privacy, you can get significantly better guarantees in performance, or significantly better performance than epsilon 0 algorithms. So now we'll take a break for 10 minutes, I guess. 10 minutes? 10 minutes.
All right. Okay, everybody, we're going to get started because we have as I mentioned before, opening remarks at 5 o'clock sharp in something A, not ballroom. Hallway? Lecture hall A. There we go. Thanks. Okay, so we're going to jump right back into it. This part will be roughly an hour with about 10 minutes for questions, so please hold your questions till the end. Thanks.
Welcome back. I hope you had a good break. Before, just to kind of recap what we looked at before, is that, you know, what I've presented before is really kind of more about the theory of you know, looking at ERM and differential privacy, and looking at sort of what does learning theory say about differential privacy. But if you know, if you want to actually run these things at scale on large systems, you have large problems. You want to do something a bit different. So what's the challenge here? So it seems like our previous story is not enough, because for, you know, large data sets, it's challenging for these sort of batch optimization methods. I can't get to the exact argmin of my objective function. So now I need to actually dig into how I'm doing the optimization. So there's more work, so that's good for papers, but maybe, you know, it's sad for graduate students. You're not done yet, you can't graduate. Okay, so using more data can also help with our trade-offs look better. Remember, so we had the triangle that Kamalika presented. There's privacy and accuracy and sample size. So if I just boost up the sample size, I should be able to get, you know, privacy and accuracy. It's like having your cake and eating it too. And then the other thing is, you know, the typical methods for doing, you know, large-scale optimization are kind of operate in an online way. So this might involve doing multiple releases. So there's some potential, if I reveal the insides of what's going on in my optimization methods, that I could be losing more privacy over time, because as Kamalika said, you know, the privacy erodes over multiple releases. So the goal is a bit different than before. Instead of saying guaranteeing privacy using the setup of the learning problem, or the sort of statistical problem, we want to guarantee privacy using the actual optimization algorithm itself. So I think it's fairly uncontroversial to say that stochastic gradient descent is somewhat popular in machine learning. It's, you know, there are a few papers. The nice thing is stochastic gradients are, you know, they're already random, right? So somehow you're already taking a noisy gradient step, so maybe you might think it's already private, or at least it could compatible with guaranteeing additional privacy, and that's true in a pretty strong sense. And the other thing is, but the problem is, of course, that these, in SGD, I keep updating my predictor variable, or updating the weights in my network, and these updates might be leaking information about the training data. So how does non-private SGD work? This is just for context, so we're all on the same page. So here's my, you know, say ERM objective, just for illustration purposes. So what do? I start out at some point. I grab a random training sample, IT, at time t. Then I compute the gradient of my loss function, of my objective function, and then I take a gradient step according to some learning rate eta t, and I project back onto some set, possibly just set script w there, right? And then I either publish my last iterate, or maybe I do an average of the last alpha t iterates or something like that. But, you know, basically this is regular SGD. So maybe it's not surprising that, you know, certainly one way you can introduce differential privacy into SGD is to just make noisy gradients. So what have I done here? It's the same algorithm before, but now when I pick a random data point, I generate a noise vector zt according to some distribution p of z, and this distribution is chosen according to the sensitivity of the gradient function to guarantee either epsilon or epsilon delta differential privacy. So if you wanted to guarantee, say, epsilon delta differential privacy, you could add IID Gaussian noise, or if you wanted to have epsilon differential privacy, you could generate that noise whose density scales exponentially with the distance, so that vector analog of the Laplace distribution. And so then I just, okay, now instead of taking my regular gradient step, I have this g hat, which is a privatized gradient step, which is just add zt to the regular gradient. and then I just take a step there, again with the same, maybe with the same type of learning rate, and again publish the output. So that's one way to introduce differential privacy into stochastic gradient descent. I just add noise to the gradient. So, again, here are the two noise distributions I could use, and they guarantee different types of privacy. So one is I could choose a noise vector that's proportional to e to the, some linear term times epsilon times the norm of the noise. So that's a vector analog of the Laplace distribution. Or I could choose Gaussian noise, which is easier to do for undergrads, as I found. It's epsilon, again, this guarantees epsilon delta differential privacy, right? So the key is we have to choose the noise according to the sensitivity of the gradient function. So I take my objective function that I'm going to be minimizing over, and I look at the worst case between distributions, databases D and D prime. I look at over all possible states that I could be at, intermediate state predictors I could look at, and I look at the worst case over that and over all pairs of databases which are neighboring. And so if you can come up with a bound, sometimes it's a crude bound, then you can set the epsilon and delta accordingly in these two mechanisms. Of course, this will also depend on all sorts of other properties about your objective function. So if you're looking at your loss function, and you need a Lipschitz parameter, and so on and so forth. So that's adding noise. A different way of guaranteeing a differential privacy is to essentially it looks similar. Basically, I'm going to do a random selection. I think of it as being different because it's not explicitly doing additive noise. So what I could do is I could compute. Again, I pick a random data point from my data set. I compute the gradient of the objective function at that data point. And then I'll just, taking that as a center, I might choose a random direction in which to do a gradient step that's somehow biased towards my true gradient. And so the point is that it should be, say, biased towards the true gradient that I calculated, but not be an unbiased estimate of that true gradient, right? So I don't want to, I want to have in expectation that the gradient step that I take be the true gradient step. So you can do this too, and so how does that work? This is sort of picture here. You kind of, the blue thing is the direction of the gradient. It's some probability you decide to go in the complete opposite direction, which is also something that undergrads seem to do. And then, and if you go in the blue direction, then you kind of pick uniformly in that hemisphere. And if you go in the red direction, the opposite direction, you pick uniformly in that hemisphere. And if you churn through things with this, you get and you have some control of the gradient norms. This will come back later when we talk about deep learning. Then we can guarantee differential privacy here. So we have two different pictures within the stochastic gradient descent of how to make your gradient estimates differentially private. One is to add noise, which is zero mean noise. And we're going to choose that using the sensitivity of the gradient. So we have to calculate the sensitivity of the gradient. And the other is to use this sort of randomly chosen gradient direction. And so there you need to control the norm of the gradient. So depending on what you have better sense of, what you have better control over or better ways of bounding, you might use one or the other. Both of these methods guarantee differential privacy at each iteration, and each iteration is only using one data point. So if I look at say doing one pass through the data, I'm only touching each data point once. So my privacy guarantees are not increasing unless I do multiple passes. As long as we ensure that the noisy gradient that we take, or the random gradient that we take for differential privacy, is unbiased, so that is an expectation is equal to the true gradient, then that makes the convergence proofs more easier. If they were biased, you'd probably have to do a fair bit more work. So that's like in theory, right? So in theory, I take one point and I do one gradient step, and I take another point and do another gradient step. And this would seem to work. Like adding additional noise is good because there's sort of a folk theorem that we have in the back of our mind saying stochastic gradient descent is robust to noise. And that's true up to a point. If I really wanted to add a ton of noise to all of my gradients, you'll still get garbage. So, no free lunch in practice. So there are a couple of different solutions you can do. Like one idea is I could do, say, n passes through the data instead of doing one pass through the data. And hypothetically, I mean theoretically, this actually works quite well. And so you can, this shows that doing more passes through the data will help you. And that's a standard trick that we also do to get better performance in gradient descent. Then you can also do things like mini batching. That's of course in all your favorite tricks there. And the third approach, which we'll talk about a little bit next, and then Kamalika will talk about a bit later, is to essentially take the gradient algorithm you have already and do a better analysis of it to show that actually the privacy that you're getting out of this method is significantly better than what the bound says. The bound says that you calculated in terms of the noise. Because remember, all of these log likelihood ratio bounds are just upper bounds on this log likelihood ratio. So it doesn't say what the gap is between the actual quantity of interest and the upper bound. So one of these kind of tricks is, one thing that you might do in general is to say sample a subset of your database, like taking a mini batch, but also just running an algorithm on multiple subsets of your database. So if I give you a differentially private algorithm, which is epsilon differentially private, in this case epsilon is less than 1, and if I sample a fraction of the entries of the database and run my algorithm on actually a subset of the database, randomly chosen, so this is the randomization in the selection is very important to make this actually work. Like, this is the key thing. So this random selection in stochastic gradient descent is actually helping you. And if I run my algorithm on those, then you can prove that the differentially private algorithm actually guarantees 2 gamma epsilon differential privacy. So if gamma is less than half, you're not taking half of your data set and then doing that, you're getting a better bound. And then you can leverage this in several different ways to show that stochastic gradient descent can work a lot better with a better privacy parameter. So just to summarize this thing about stochastic gradient descent, so it's pretty easy to make stochastic gradient descent differentially private by adding appropriate noise. You can come up with your own favorite randomization method for the gradient and then prove an epsilon delta that guarantees epsilon delta differential privacy, and it might work very well for you. So, I just gave 2 examples. As long as we keep the gradient estimates unbiased, this makes convergence more straightforward. And we can do a lot of tricks to reduce the instability caused by adding noise. And actually, these tricks can, in themselves, help with the performance. That is, I can guarantee make better privacy guarantees if I use some of these tricks. And in particular, if I use this random sampling, I can really this is one of the tricks is this random subsampling of the data. So I think this works for general gradient descent procedures, not just empirical risk minimization. So this is the key driver behind understanding how to do larger scale applications, which we'll talk about later when we talk about differentially private deep learning. So if I'm going to be running through my data several times, I have to do some kind of tracking of the total privacy risk. If I'm going to be doing very complicated interactions with my data set, then I need to be a bit careful. And one thing that helps us here is this post-processing invariance, right? So post-processing invariance tells us that if I have a differentially private method and I publish something out of the data set with that, then any post-processing you do of that thing after the privacy barrier is going to keep the same privacy guarantee. But if I'm going to do multiple releases out of this data set, I want to know get a sense of what the total privacy loss is. And so, this happens all the time in machine learning. You might do some pre-processing of your data and then go back to the data set and train a classifier and also do some cross-validation. You're constantly going and mucking around with the data set. So you're going to be leaking different amounts of epsilons and deltas in each of these parameters. So what's the total privacy loss? So the composition theorem that we saw before is this graceful degradation of privacy says, you just sum up all the epsilons and sum up all the deltas, and that's your total privacy risk. This has the advantage of being nice and clean, but has the disadvantage of saying, well, it looks like you're not guaranteeing very much privacy after doing just a little bit of processing. So the question is, what can we do here? So So total composition theorems, the existing composition theorem says that in this example where I go back to the training data multiple times, that I'm going to incur the sum of all the epsilons and the sum of all the deltas. And even just taking this, this means that if I'm going to know that I'm going to be doing some differentially private, machine learning on some data, then I might start out with a privacy budget. There's like a total cap of the epsilon and delta that I'm allowed to use. Maybe the lawyers tell me that I should choose this epsilon delta. Remember, I'm not going to tell you what epsilon and delta to choose. It's not my place. If you're given a total epsilon and delta, the question is how do you allocate across the different stages of your pipeline where you're going to incur more privacy risk? And this is not trivial. So I might be able to get away with like really terrible features or noisy features, but I really need to make my training method not noisy at all. It has to be very good. Or maybe I want really clean features, and then actually I don't, my optimization for my training can be somewhat loose. And again, remember, all of these things depend very strongly on the actual data set that you have. So being able to assess how you're going to allocate these across different stages is an open question that people have been looking at. And I think it's a pretty interesting question for practice and also for theory, if we can get some actual theory about this. Okay, so if I want to do better than this sort of graceful composition, then I have to have a closer look at what epsilon and delta mean in terms of the actual mechanism. So let's look at the example of adding Gaussian noise, right? If I want to add Gaussian noise, what we said before is choose a noise of this as a function of epsilon and delta like this, and we'll guarantee epsilon delta differential privacy. But I could flip that around. I could say, what if I add noise of variance sigma squared? What is the epsilon and delta that I get for that sigma squared? And so it turns out there's actually a whole spectrum of epsilons and deltas that you can get. So many combinations of epsilon and delta will lead to the same sigma squared for your Gaussian. And what's going on here is you're trading off the epsilon guarantee, which bounds this log likelihood ratio, and the delta guarantee, which is saying there's a probability that something, that you'd violate this log likelihood ratio condition. So if I set my thresholds for my Gaussian, so here I have two Gaussians corresponding to database D and D prime. If I look at the ratio at a point between these two curves, within the unshaded region, that ratio is bounded by e to the epsilon. So that's saying the log likelihood ratio is bounded by epsilon. So that's my epsilon guarantee is happening in the unshaded region. And then in the tails of the distribution, that's where delta happens. If I drew something in the tail of the distribution, then I'm in the delta event. And we can see here is that the delta event is not catastrophic, for one thing. It's still very unlikely to choose like a thing way out in the tails. So this summarization that you get by delta is maybe a little bit misleading. So we should hopefully be able to do something different. If I set my boundaries somewhere else, I could increase delta and get a stronger guarantee on epsilon. I'm at better control in the unshaded region of the log likelihood ratio. But in order to do that, to get this smaller epsilon, I'm going to incur a larger delta. So all of this is, and this happens not just for Gaussian noise. I mean, it happens for sort of any mechanism that you can look at. You can see, well, if it gives an epsilon delta guarantee, how is it trading off epsilon and delta? So this is actually all happening because the privacy loss itself is a random variable, and differential privacy is only giving you an upper bound on this random variable. So if I look at this Gaussian mechanism and I say, what are all the epsilon delta combinations that I can get for a particular value of the variance of the Gaussian, we get a curve. This is log delta versus epsilon. In particular, what its curve is saying is that if I want a particular level delta, for example, I have to choose a certain minimum epsilon if I'm going to use this noise variance. So that's what the trade-off is giving you. And so if I want to look instead at this log likelihood ratio, and suppose I actually have data set D, then I want to know how small is this actual log likelihood ratio, which I draw with the probability that, or the density that the output of my algorithm equals a particular value T. So this is a function of the database D and D prime. Like, how can I control, or how do I understand this random variable itself? So Right, so the privacy loss is a random variable, and so we actually have to bound it over all d and d prime. So I have to take a max over all d and d prime, so there's like a slightly even more complicated random variable. But this is for a particular algorithm A. If I have multiple algorithms that I'm running on my data set, that's kind of like producing multiple draws of this random variable for different values of AI. So for example, if I ran the same algorithm, just for argument's sake, on the data set a bunch of times, that's like sampling IID from this. My actual privacy loss I experience is going to be related to the IID sampling of this random variable that depends on the data set. And so we can then use concentration of measure arguments to show that the loss is actually significantly closer to its expectation. And so that's one way of trying to improve the total epsilon delta privacy guarantees you can get. And this goes under the rubric of strong composition bounds. So here, what I can tell you is that I'm going to tell you that, oh, you have some methods. I'm not going to tell you what they're doing or what they're for, but I'm going to tell you each of these methods is guaranteeing you epsilon delta differential privacy. That's what you have. And then I want to say, okay, just knowing that I have outputs from k epsilon delta algorithms, what can I say about the total privacy loss? And it turns out, again, much like the case with just a single Gaussian mechanism, you get a whole host of total epsilon delta guarantees, which you can characterize using some hairy equations. But what this is doing is saying that the composition means that the actual total privacy risk that you're going to experience is, with a reasonable probability, not as bad as the worst case would guarantee. So you can do significantly better than this linear increase where the naive composition would say, oh, it's k epsilon times k delta, and this is significantly better. But if I want to do even better in terms of accounting for these noise variables, then I need to understand not just what epsilon and delta my algorithm is guaranteeing me, but what is the algorithm actually doing? That is, what is the noise or where is the randomization being introduced? And by analyzing that randomization in a more careful way, then we will be able to get better composition bounds. And that's what Kamalika will talk about now.
So thanks, Anand. So far, Anand has been telling you about what happens when you have a bunch of different components, and you know that each component gives you epsilon I, delta I differential privacy. Now, what can you get at the end? Okay. Now, what I'm going to talk about is a set of recent methods introduced by Abadi et al. In 2016, where you could look under the hood to see what these mechanisms were doing, and then use that to get, better composition bounds, what is called better composition bounds. And obviously this is going to be more efficient than the composition theorems, because specific mechanisms, so the composition theorems are sort of worst case over all epsilon delta differentially private mechanisms, whereas these specific mechanisms might have better properties which make them compose better. Okay, so that's what we are going to talk about next. So how do we do this direct composition? Well, remember the privacy loss random variable that Anand talked about a couple of slides ago. If you have two data sets, D and D prime, that differ in a single record, and a mechanism A, then this is the privacy loss random variable. It takes the value log of the ratio of the likelihoods that P A of D is equal to T versus A of D prime is equal to T, and the likelihood of this value is P of P that A of D equal to T. Okay, and the properties of Z, D, and D prime is related to the privacy loss of A, right? So, for example, if you look at the maximum absolute value that Z, D prime can take over all D and D prime pairs which differ in a single record, and if you can show that this maximum absolute value is at most epsilon, then the mechanism A would be epsilon 0 differentially private. Okay, so we can look at these variables and we can analyze them directly. The challenge here, however, is to reason over the worst cases over all D and D prime pairs, right? So you can, if you look at, you can look at one Z D D prime and you can analyze it, but the challenge is what happens over the worst case, right? To look at the max over D D prime. And the key idea in this Abadi et al. Paper was to use moment generating functions of Z to make this reasoning much easier. Okay, so that's where kind of the name comes from, moments accountant. Okay, so how do we account for moments? So we are going to do this in 3 steps. Suppose you have some private data set and you have, you have differentially private algorithms A1, A2, A3, and so on touching it, right? So first we will calculate the moment generating functions for each of these, at each of these individual steps, right? For A1, A2, and so on. Second, we are going to compose these moments, okay? And remember, we are right now in the domain of moments. So finally, we are going to use these moments to calculate the final, eventually the final privacy parameters, okay? So first, let's look at stepwise moments. We define the stepwise moment at time t. So at time t, you're using algorithm A sub t. The stepwise moment at time t of A sub t at any parameter s is the supremum over all d and d prime that differ in a single record, log of the moment generating function of z d d prime evaluated at s. Okay, so this is, remember, expectation of e to the s z is the moment generating function. So log of this moment generating function evaluated at s. Okay, so how are we going to compose this? So these are the moments at each step. How are we going to compose them? Well, Abadi et al. Show this very general theorem. Suppose you have mechanisms A1 to AT. For any s, the moment at s of A, which is the union of A1 to AT, is at most the sum of the moments of the individual steps. Okay, so alpha A of S is sum over T goes from 1 to T, alpha AT of S. Okay, so now you can get the moment of A. And finally, you can, the third step is, we are still in the realm of moments. The third step is to do the final privacy parameter calculation. Again, Abadi et al. Showed a theorem which shows that the privacy calculation can be done by solving the following equation. So the equation is your delta is the minimum over S, e to the alpha A of S minus S times epsilon. Okay, so here, the idea is you can use this theorem to find, if you have a delta budget, so if you have, if you have some restriction which says delta cannot go below a certain amount, then you can find the best epsilon for this delta. Or if you have an epsilon budget which says that, oh, your epsilon cannot go above a certain amount, then you can, then you can find the best delta given this particular epsilon. So you can use this relationship to find the, best, either the best delta for a given epsilon or the best epsilon for a given delta. And so how do we actually do it? Well, in some cases, this can be done in closed form. So there are some, especially simple mechanisms where you can do it in closed form. But in general, we can do it by a grid search, right? So in general, what could happen is that these AIs could even not be the same mechanism, right? So one could be a Laplace mechanism, one could be a Gaussian, one could be something more complicated. So in general, we would need to do this over by using a grid search over the parameter S. Okay, so just as a quick example, suppose we are trying to compose the Gaussian mechanism, and here each step is a Gaussian mechanism. Again, this is a very special simplified case, and AT answers a query with global sensitivity 1 by using normal 0-1 noise. Okay, and if you use if you do some algebra, what you will find is that the moment function, the alpha AT of S, is S times S plus 1 over 2. And so these are our stepwise moments. We can compose them to get alpha A of S is capital T times S plus 1 over 2, where capital T is the number of times you were using the Gaussian mechanism. And then finally, you can solve this equation we talked about to find the optimal, optimal delta for a given epsilon or vice versa. And here notice that this particular equation can be solved in closed form because the Gaussian mechanism has a particularly nice, the moments of the Gaussian mechanism have a particularly nice functional form, but in general you might have to use grid search. when you have complex mechanisms. Okay? So how does this compare? So here is a figure from Abadi et al., where in the x-axis we have now rounds of composition. So this is the capital T that I was talking about. And on the y-axis we have epsilon. Okay? And what we are comparing is what is the epsilon we get after starting with a certain Gaussian mechanism and then composing for a certain number of rounds. Okay? And the black circle is the moments accountant. This is the method I just told you about. And the black square is Dwark, Rothblum, and Vadhan in 2010. So this is a strong composition method which is better than linear. Okay? And what we see over here is that the gain from using moments accountant is quite a bit. Okay? So, so this is how the epsilon looks like. And this is and all of this is for a fixed delta. Okay? Now, the next question is that how is it going to do on real data? Here is an example from Park, Fowles, Chaudhary, and Welling in 2017. What you are looking at here is, test log likelihood per data point as a function of epsilon for expectation maximization for mixtures of Gaussians. Okay? And here, each of the parameters were perturbed using the Gaussian mechanism. Okay? So here, the dark blue line is linear composition, which is kind of the worst case and the very naive thing we talked about in the beginning. The pink line is advanced composition. This is Dwark, Rothblum, and Vadhan. And finally, the cyan line is moments accountant, and here the red line is an approximation to moments accountant, which I won't go into right now. And what you see is that the cyan line, so here above is better, because this you're looking at log likelihood, but what you see is that the cyan line performs better, right? So so the privacy accuracy trade-off that you have over here for a fixed sample size is better for moments accountant. Okay? So in summary, when you want to design practical machine learning algorithms, what you need to do is you often need to look at data many times, right? Because there are many times in the many points in the machine learning pipeline where you need to look at data, and certain properties of differential privacy makes this process smooth. So for example, post-processing invariance means that we just have to track the cumulative privacy loss. We don't need to worry about what happens after things cross the privacy barrier. Good composition, so we talked about some naive composition methods, but there are better composition methods which use the fact that the actual privacy loss might behave much better than the worst case bound that we have seen before. And I talked about a new method, the moments accountant, for tracking the actual privacy loss more accurately than the naive, the naive and also the other composition theorems, and showed that it could lead to better privacy guarantees and better privacy accuracy trade-offs. Okay? So next, what I am going to do is I'm going to go ahead and talk about a couple of case studies of these methods that I have talked about to modern machine learning, right? So far we have talked about tools for designing differentially private algorithms and for designing differentially private machine learning algorithms. We will now look at a couple of case studies, okay? So when is differential privacy practical, okay? So remember, we have been trying to be, we have been talking about this for a while. Differential privacy is best suited for understanding things like population level statistics and structure. So what we want to get out is inference about the population. So we want to make accurate inference about the underlying population, but we don't want our inferences to depend strongly on individuals in the data. And so what happens is in a lot of modern machine learning applications, we do have really large data sets, right? So we do have really large sample sizes, which is in fact a good thing for privacy because it means that we can get a good privacy accuracy trade-off when our sample sizes are large, okay? And also to build and analyze, large machine learning systems and pipelines, we have to leverage post-processing invariance and composition properties. Okay. So where is differential privacy used in practice? So here are like three major important examples. Google has a system called Rapport, which tracks user behavior statistics in Chrome, certain user statistics in Chrome. Apple has has implemented differential privacy in their iOS 10, and this particular implementation also looks at user statistics, right? It transmits user statistics with differential privacy back to Apple. And in the 2020 census, in fact, they will, in the United States Census, is going to use differential privacy. So, so these are some, high-profile use cases of differential privacy in practice. Okay, but the thing to note here is that a lot of these high-profile usages are, in fact, mostly focused on count and average statistics, right? So, so Rapport essentially transmits user statistics back, and same with iOS, and in Sensor they would also be looking at various kinds of counts and various kind of average statistics. Okay. In contrast, machine learning is actually quite different, right? So differentially private machine learning is in fact quite different, and things are in fact much more complicated here, right? So they're complicated in several ways. So one reason why they're complicated is because real machine learning algorithms are really complicated, right? So machine learning, when you develop a machine learning algorithm, it involves multi-stage pipelines, parameter tuning. Very often we need to do some exploratory data analysis when basically play around with data before you decide what tool you're going to use, what kind of classifier or architecture you're going to use. And finally, a lot of modern machine learning approaches, for example, deep learning, have a lot of parameters, and there is not a lot of theoretical guidance on how to set them, so you don't know how to set them ahead of time. Okay? And what I will do is today I'll discuss two recent examples: differentially private deep learning, which was done by this the Abadi et al. Paper, and a little bit of work on differentially private Bayesian inference, which was done by a group of different people. Okay, so how do we do differentially private deep learning? The main idea is that we are going to train a deep network using differentially private stochastic gradient descent, and then use the moments accountant to track privacy loss. So you have a standard neural network, you train it using private stochastic gradient descent, and then you do some tricks on top of it. Okay, and they used a lot of additional components which made the algorithm, which helped the performance of the algorithm. Things like gradient clipping, which can help reduce the sensitivity of the gradient, mini batching, which helps, and data augmentation, and so on and so forth. Okay? So here is kind of what the algorithm looks like. You have a private data set D, and what the algorithm would do is it would select a random lot, which is essentially a group of samples, and then they would use subsample batches from this lot to compute the gradient. So I don't I don't want to go into the details of how exactly this was done, but they had these lots, and then they would subsample to compute the gradients. These gradients will be then made differentially private by clipping and then adding noise. Right? And then the differentially private gradients will be, on the one hand, they will be sent across the privacy barrier, where it would be used to update the parameters of the network, right? So the network would start with some weights, and then you use the private data to get these differentially private gradients, and then these gradients would be used to update the weights of the network. Another thing that was going on at the same time was that the clipped gradients would also be, kind of transmitted. So, the parameters of the clipped gradient would also be transmitted back to the moments accountant algorithm, which will also keep track of the privacy loss and in a very accurate way. Okay? So this is essentially the overview. And how does it work? Well, here are some empirical results where you are looking at, on the x-axis, you have the number of epochs, and on the y-axis you have you have accuracy, and each of these is for a different epsilon. Essentially what they found, so they tried it on MNIST and CFAR, and what they found was training and test error comes quite close to baseline non-private deep learning methods. Okay? But to get moderate loss in performance, epsilon delta had to be they were not negligible, right? So they had to be non-negligible. Okay, so yeah, they had to be non-negligible. So this was again an excellent proof of concept for differential privacy in deep neural networks, and there are lots of open questions. So for example, one would be, this just looked at a standard neural network. Are there better architectures? So for example, recurrent neural networks or GANs, and there has been some recent work on archive on some of these architectures, but like getting them to work almost as well as non-private deep learning still remains an open question. Okay. A second open question is, what about regularization methods which are suited for deep learning? For example, dropout, can they also help with privacy? Again, there has been a little bit of work on this by Avradeep, but some of that, some of it remains. Okay. And then finally, what are some good rules of thumb for choosing, lot size or batch size, learning rates, and things like that? Okay, so next, let us look a little bit at differentially private Bayesian inference. So what is Bayesian inference? Again, here the idea is that you have a whole bunch of observations, data x1, x2, and so on, and you have a model class theta, which are related through a likelihood p of x given theta, right? You begin with a prior over theta, which tells you, your prior belief, right? So you have some beliefs about theta, which are captured by a prior. You get your observations, and using your observations, you can update your prior into a posterior. Okay? So a couple of things to note. So one of the things to note is that a posterior is actually gives you also, it's not just about a single point estimate, but the whole posterior is going to give you some idea about your confidence, right? So for example, if you have some, if you start with a prior and you get 5 data points which look a certain way, whereas if you get 50 data points which look the same way, in the second case your posterior is you're going to be much more confident, and your posterior is going to be a lot more peaked, right? So what Bayesian essentially what Bayesian inference does is it tries to maintain the posterior in some way or the other, and what we would be looking at doing is to maintain differentially private approximations to the full posterior. So there's been a fair bit of work on differentially private Bayesian inference by now, and the work is kind of divided into 3 general classes of methods, right? The first is general methods for approximating the private posterior distribution. In the special case of exponential families, as it happens, we can do much better. And then finally, variational inference. So let me begin with how to, the general methods for for approximating a posterior privately. Okay, so how to make a posterior private? A very natural, a natural thing that suggests itself is direct posterior sampling, right? So very often what happens is, you have a posterior, you can't really maintain every parameter of the posterior because it will be, intractable. So what happens is, even in the non-private case, you would maintain a few samples from the posterior, or even, let's say, drawing a single sample from the posterior, right? And that you would use that as a representation to your posterior, okay? And so the question is, since you're not drawing a lot of, since you're not maintaining the entire posterior, you're just drawing a single sample, well, does that process preserve differential privacy? And this was studied by Dimitrakakis et al. In 2014, and they looked at some very general situations, but essentially what they could show, right? So overall conclusion from their paper was that direct posterior sampling is not differentially private unless the prior is quite restrictive, right? And the reason why this happens is in many cases, so they're not differentially private. When I say not differentially private, I mean for many common prior posterior pairs, right? And the reason why this happens is that in many cases, the likelihood ratios, when you change one record, could become unbounded, right? So just to give you a pictorial representation, so here, the red and blue curves are the posteriors when you change one person's value, and if you look at the black kind of vertical line on the tail, you see that the ratios are actually quite high over there, and this happens. This happens for quite a few common distributions, okay? A slight plug that the answer changes a fair bit under a new relaxation called Renyi differential privacy. This is a paper that we have in this year's NIPS, so if you're interested, you can go check out our poster. Okay, so so direct sampling doesn't often work. So how do we make the posterior private? Okay, so this was again looked at by Wang et al. And they came up with a method called the one posterior sample or OPS method, which was inspired by the exponential mechanism which we had looked at earlier. Okay, so here is what they observed. So they observed that if you look at these posteriors, I mean, it is true that often there are points at which the likelihood ratio is unbounded. However, if you move away from the tails, right, if you move away from the tails for a lot of common prior posterior pairs, if you move away from the tails and if you move towards the middle, there are areas in which the log likelihood ratio is non-bounded. Okay, so what they wanted to do is, what they suggested doing was you truncate the posterior so that you are in the region where the log likelihood ratios are not too large, and then you flatten them out, right, by raising them to a higher temperature. Okay, and so so that gives you a certain distribution, and you just sample from this distribution. Okay, so this was so this is how that is how you could do it. Okay, so the advantage of this is, in fact, it's actually really quite general, and they could show that it applies to a lot of interesting prior posterior pairs. However, there are a few pitfalls, right? So one of the pitfalls is that unless you are sampling from exactly this truncated posterior at a high temperature, your algorithm will not be differentially private, right? And for example, so in practice, what people do is they use MCMC to sample from these posteriors. Those MCMC processes may not guarantee differential privacy. I mean, unless you do a separate analysis by yourself, and that itself is pretty hard. Okay. And this again ties back to, remember when we talked about the exponential mechanism, we briefly talked about how doing it in a continuous domain sometimes leads to intractability, right? And which is a problem even for privacy, because unless you are sampling from this exact distribution, you're not getting privacy. Okay. Another pitfall that this mechanism has is, in certain cases, what could happen is you could have low statistical efficiency even when your n is large, right? And what this picture is showing over here is, in the x-axis, you have the number of data points in a log scale, and in the y-axis, you have the L1 error to the right, to the true posterior. And what you see is, so the blue line is essentially the L1 error to the true parameter. L1 error to the true parameter, not the true posterior. So what you see over here, the blue line is the non-private. So if you sample from the non-private posterior, this is what you would get. And the green line is one posterior sample. So you see, if you increase the number of, if you keep increasing the number of samples, the gap, does not really narrow. Okay. And in fact, the reason why this happens is because of raising the, because you're raising the posterior to a higher temperature, right? So, n samples are sort of equivalent to n epsilon samples, roughly. Okay. Another, way to make the posterior private was, again done by Wang et al., which solves the intractability problem. And here what they would do is they would say, okay, so we have this OPS distribution, and now we will just approximate it via a stochastic gradient MCMC. So, approaches like stochastic gradient longevity dynamics and so on. And, obviously the noise here, the advantage here was that the noise added during the stochastic gradient process, it contributes to privacy. However, one of the things they found was that this was even less statistically efficient than the exact OPS. Okay, so far we have looked at some general methods for approximating the private posterior. As it happens, in the special case of exponential families, you can do a lot better, and this is what we would talk about next. Okay. So just a quick reminder of what exponential families are. So if you have an exponential family posterior, this is what it's going to look like. P of theta given x would be proportional to e to the eta of theta times sum over I t of xi minus some things. So here the important thing to remember is that there are some functions of theta, but this posterior depends on the observations which are private through just this one sufficient statistic t. right? So if you didn't know the data and somebody just gave you t of x, you would be fine, okay? And this is what one can exploit. So this is what one can exploit, and this was done by Zhang, Rubinstein, and Dimitrakakis, and Fowles et al. At more or less the same time. So this is what you can exploit. So if your sufficient statistic t is bounded, then you just add noise to sum over I t of xi to get a private version t prime, right? And here you could use like Laplace noise or Gaussian noise, and then you sample from this perturb posterior, right? So the perturb posterior, where instead of t you are using t prime, okay? And so this is the algorithm. How does it work? Well, this algorithm is in fact statistically efficient, okay? So if you look back at this figure, so this is the same figure I talked about a little bit earlier with OPS and non-private posterior. Now look at the red line. The red line is this algorithm that I just talked about. And if you look closely, you will see that as n grows and grows, the red line will slowly come and merge with the blue line, right? And what this means is that the private posterior is converging to the true posterior, okay? And how about on real data? Well, what we find is that the performance is, of course, worse than non-private. This is something we can expect, but it's a little bit better than OPS, okay? And since it works, quite well, what we could do is we could use this to do inference in relatively complex systems and building up on this method. So for example, the figure that I am showing is for doing time series clustering in hidden Markov models using this, using repeated applications of this method, okay? Okay, so I have talked about posterior sampling. Finally, let me tell you a little bit about variational inference. So this is, so differentially private variational inference. Here again, the main idea is that you start, I won't go into the details, but essentially you start with a stochastic version of variational inference, and there are lots of stochastic variational inference style methods, and then you make each step private by adding Laplace noise. So it's a bit like stochastic gradient descent. So you make each step private by adding Laplace noise, and then you can use moments accountant as well as subsampling to track the privacy loss. And this was done by Yalko et al., and this is a figure from their paper on differentially private logistic regression, as well as Park et al. Okay. And so, essentially it's a lot like, the way you do differentially private deep learning. You use a stochastic gradient descent, and then you can use moments accountant and subsampling and also gradient clipping, tricks like this to keep, to ensure that you have good privacy loss, okay? So, in summary, we have talked about two specific examples of differentially private complex machine learning algorithms, right, where the ideas that we talked about earlier in the tutorial come together to give you these complex machine learning kind of pipelines. And these two that we have talked about are deep learning and Bayesian inference. And this is, we are almost at the end. So in summary, what we have looked at is, basic differential privacy. We have looked at the definitions and mechanisms. We have looked at differential privacy and, statistical learning, and we have looked at two main methods, so ERM and stochastic gradient descent. We have looked at tools for composition and tracking privacy loss efficiently, which are building blocks. Essential building blocks in more complex differentially private machine learning systems. And finally, we have looked at two applications or case studies in deep learning as well as Bayesian inference. There are many things that we haven't covered. So an example would be, synthetic data generation. So things like differentially private data release or releasing synthetic data. Interactive data analysis. There is a lot of statistical estimation theory and limits that tell you how, how minimax risk behaves under differential when you also add differential privacy. We haven't gone into that for the purpose of this tutorial. There is also a lot of work on, feature learning and dimensionality reduction. And of course, there are many, many systems questions when you want to deploy these methods on a large scale, okay? And here are a couple of more resources. There was a big data workshop, a big data and differential privacy workshop at the Simons Institute a few years ago. You can, that The talks from the workshop has a lot of, there are a lot of nice talks that you can, videos that you could look at. And there's a recent monograph by Dwark and Roth, which is also available online. So finally, what we talked about today was we looked at, the final takeaways that, things you could take away from this tutorial is we looked at the risk, at how differential privacy measures risk incurred by algorithms operating on private data, and we talked about, when to use differential privacy. We looked at how commonly used tools in machine learning can be made differentially private. We looked at how we can efficiently track total privacy loss to enable more complex private algorithms. And finally, there's still a lot of work to be done in terms of both theory and practice. Okay, and with this, I will end the tutorial.
Okay, great. So we have 10 or 15 minutes for questions, so if you can queue up on either of the microphones, I think both the speakers would be happy to answer any of your questions. Oh, and reminder, 5 o'clock, opening remarks. Lecture Hall A. I remember A and not the words before it, at 5. All right, thanks, guys.
Hi, thanks. That was extremely helpful. Thanks a lot for giving that tutorial. A question I have is how to talk about values of epsilon, especially with policymakers, institutional review boards, that kind of thing.
Okay, so that's an excellent question, and so there are several ways to look at it, right? So one way is that you could do an economic analysis. So there's a paper by Aaron Roth and a bunch of other people who have looked at, you could do a cost-benefit analysis, and then, based on that, you could look at epsilon, right? So what is the utility cost, and and what is the benefit, and you can just find a good epsilon. Another alternative approach that people have been looking at are attacks like membership inference attacks, right? So these are attacks where, let's say you have a differentially private, output of a differentially private algorithm, and you want an adversary who has some prior knowledge to infer whether a certain person is in the data set or not. And if that attack succeeds, then, that's a bad value of epsilon, right? So you could keep doing this attack for various values of epsilon and then choose ones where attacks like this don't succeed. And again, what I would emphasize is that there aren't any great answers here. So these are some, these are two potential ways in which you could choose epsilon.
Hello, thank you for your talk. Actually, it was very understandable and useful. However, I have one basic question for you. Actually, in some time, I will participate in solving tasks that relates to your questions. I will develop predictive system for health diseases based on web data, and data privacy will be very, very important in this task. But I need to give some evidence for my managers that this task is data privacy is a really important task about in terms that you formulated now. How could you give me some advices how these attacks could be simulated, attacks to classifiers, to show that this problem actually is?
So I think the closest work that, the attacks kind of work that you're talking about is something called membership inference attacks. And there the idea is that you have a classifier or, some sort of statistic, and you have some prior knowledge, and you are trying to infer if a certain person is in the data. So there's a paper by Vitaly Shmatikov and was it Reza Shokri, I think, which was in this year's, was it this year? So if you send me an email, I can send you a reference, but there's been some recent work on this. Or if you, Google for membership inference, they have, there's a paper, and I think they also have code.
Hi, thank you for the talk. Earlier in the talk, we saw how to make methods like HGD private by adding some sort of perturbation to the stochastic gradient. What happens if we don't add such perturbation at every iteration of the algorithm, but every few iterations? Do we leak too much information? Like, does the method, is the method still differentially private?
Well, the thing to look at is when are you accessing the private data in your iteration? So you say the word iteration, it can mean, yes, I'm going to go grab another data point from my data set and then run some iteration, but you could also be doing some internal iterations which don't use fresh data. So you will be leaking some privacy if you are grabbing fresh data for that iteration, if you don't introduce any randomization. So I think that's the best I can give that, yeah.
Thank you.
Thank you very much for your interesting tutorial. Would you be able to share the list of papers that you referenced in the slides? Because they only had reference.
Yeah, we have a bib tech that will get populated and then we'll post it with the slides.
Thank you.
Mhm.